All right, we're going to go ahead and skip these couple problems here. They're very similar to what we just did, and so we're going to move ahead to fractional precipitation. So fractional precipitation is a process where we're trying to separate multiple precipitates from one solution. And so let's take a look at example 28 to see an example of this. It says solid silver nitrate is slowly added to a solution that is 0.0010 molar in each sodium chloride, sodium bromide, and sodium iodide. Calculates the concentration of silver ions required to initiate precipitation of each of the following silver halides. We have silver iodide, silver bromide, and silver chloride. And you're given the KSPs for each of those. So what we're going to do is we're going to take the KSP and the concentration of chloride, bromide, and iodide, respectively, and use those to find the concentration of silver ions needed to make each of those precipitates. So if we take our Ksp expression for silver iodide, rearrange that to solve for Ag+, we see that we need at least 1.5 times 10 to the negative 13th molar concentration of silver ions to make the silver iodide. Apply that same process to the silver bromide. Again, solve for silver ions concentration. This time 3.3 times 10 to the negative 10th molar. And then for silver chloride, we need at least a concentration of 1.8 times 10 to the negative 7th molar. So what if you were actually doing this? What if you took silver chloride, a mixture of silver chloride, silver bromide, and silver iodide, and added, sodium chloride, sodium bromide, sodium iodide, and added silver nitrate to that? Which precipitate would form first? Well, hopefully you understand that the precipitate that will form first is the one that requires the smallest concentration or largest concentration of silver ions. That would be the smallest concentration. So looking at our values here, the precipitate that requires the smallest concentration of silver ions is the silver iodide. So it will form first. If you continue to add silver nitrates, then at some point, once the concentration of silver ions is at least 3.3 times 10 to the negative 10th, then the silver bromide will form. And then lastly, silver chloride would form. As it says in the book underneath the solution, we can also find the percent of the ions that remain in solution, but we're not going to do that part here. We're just going to calculate or determine rather which precipitate would form first, second, and third. So take a look at an example of this on page 788, number 37. So this time we have a solution that contains lead 2 and a solution that contains silver ions. And to that solution, I should say, it's a mixture of those two. We're going to add chloride. So it could be sodium chloride that we're adding here. That's what it says in this problem. And again, we're trying to determine which precipitate, silver chloride or lead 2 chloride, forms first. And so let's just go to that part, do that first part, letter A, and we won't worry about letter B. Go ahead and pause the video and do that now. All right, so taking a look at the Ksp expression for both of our would-be precipitates, silver chloride and lead 2 chloride, along with their Ksp values, calculated the minimum concentration of chloride needed to precipitate the lead or the silver. And so for the lead ions, we need a minimum concentration of chloride of 0.034 molar. And for the silver, to precipitate the silver ions, we need a minimum concentration of chloride of 1.2 times 10 to the negative 8th molar. So because it takes a lot less chloride to precipitate the silver than it does to precipitate out the lead from solution, the silver chloride would form first. Number 39 is similar, except that we're forming 3 different precipitates of lead, lead 2 hydroxide, lead 2 carbonate, and lead 2 sulfates. And so again, we're trying to figure out which precipitate would form first. And so the process is very similar to what we did here. And so we're just going to skip that one as well. Which brings us to our last section on simultaneous equilibrium. Take a look at example 2010 on page 781. It says we make a solution that is 0.10 molar in magnesium nitrate and 0.10 molar in aqueous ammonia, which is a weak base. Question is, will magnesium hydroxide precipitate from this solution? And you're given the Ksp for magnesium hydroxide along with the Kb for ammonia. So let's take a look at our two equilibrium systems. So we're trying to see if a precipitate of magnesium hydroxide forms. So this is slightly soluble. And so here's the equation for that particular system. And then we also have aqueous ammonia, ammonia being a weak base. So it establishes equilibrium. And this solution contains hydroxide ions. So what we need to determine is what is the concentration of the hydroxide produced from the ammonia ionization, and will that be enough along with the concentration of magnesium from the magnesium nitrate to form a precipitate. So again, we're going to calculate concentration of OH minus, concentration of Mg plus 2 is given to us already. Plug those into our Qsp expression and compare that to K. So again, just like we did recently on a test, we can use the Kb of ammonia to solve for concentration of hydroxide. So that's what's shown in the setup there. So we have, after we've assumed that x is small, we get x squared over 0.10 equals the Kb for ammonia. Solve for x, and we end up with a concentration of hydroxide produced from the ionization of ammonia of 1.3 times 10 to the negative third molar. Again, don't forget to square that, because in our Qsp expression, we have concentration of magnesium, which was 0.10, concentration of hydroxide, which was 1.3 times 10 to the negative third. Square that, multiply by magnesium's concentration, and we get a Qsp of 1.7 times 10 to the negative 7th. Compare that to the Ksp of magnesium hydroxide, which was given to us in the problem, 1.5 times 10 to the negative 11th. Looks like Qsp is greater than Ksp, therefore a precipitate will form. All right, go ahead and apply that same procedure to exercise number 47. Calculate Qsp and see if a precipitate forms. Go ahead and pause now. All right, so here's our setup. I decided to set it all up using an ice table and everything. So we have an initial concentration of ammonia, 0.080 molar. So we want to use that to find the concentration of hydroxide in that solution. So plug in our equilibrium concentrations into our Kb expression. Assume x is small. Calculate the value. Looks like we can use a 5% rule here. And x is less than 5% of 0.080, so we're good there. So take this hydroxide concentration, plug it into our Qsp expression for manganese 2 hydroxide. Once again, don't forget to square it. Concentration of manganese in the solution 0.040, and we get a Qsp of 5.8 times 10 to the negative 8th, which is greater than the Ksp for manganese 2 hydroxide, which tells us, yes, this precipitate will form. All right, that concludes this lesson. Thanks for watching.